Okay. So again, thank you very much for the invitation and for coming to lecture 2. And so I think after these 3 lectures, you will be very tired of me. Anyway, so what I would like to discuss today is some recent results we have done on extrinsic geometric flows, in particular the inverse mean curvature flow and the Gauss curvature flow, and it will be on the complete non-compact setting. But in the time being, let me just give a small introduction in general. So this talk today has to do with the evolution of hypersurfaces and dimensional hypersurfaces embedded in Rn+1, so it's called dimension 1, by flows where each point on the hypersurface moves in the right normal direction, whatever makes the problem to be parabolic, by a speed which is a function of the curvatures of the hypersurface. And so from the PD point of view, this evolution, these geometric flows provide interesting models of nonlinear equations, and sometimes we attack them with pure PD points, with pure PD techniques, but sometimes a little bit of geometry helps in the calculation and the outcome. Okay, so again, as I said, I will discuss the inverse mean curvature flow and the evolution by powers of Gaussian curvature, and I will study mostly hypersurface that can be written as graphs over Rn, and so they are complete non-compact. So again, the typical examples of such flows is the mean curvature flow, that's the most known, which I will discuss only very briefly at the beginning. And here you evolve by, your speed is the mean curvature, everybody knows it's the sum of the principal curvatures. The inverse mean curvature flow, where you move by 1 over the mean curvature, is the opposite direction. Now the Gauss curvature flow, the classic one of power 1, you move by the product, by the Gaussian curvature, which is the product of the principal curvatures, or we can take any power of it. And other flows is the harmonic mean curvature flow by the harmonic mean of the principal curvature, or you can take, these are flows of homogeneous of degree 1, which are where the speed are ratio of elementary successive polynomials of principal curvatures. So these are some typical examples. All right. We're interested in the non-compact case. So most of the work that has been done, at least in the more classical sense, have to do with compact surfaces, although some results that have been done are local. But so today we're going to be working with hypersurfaces that extend all the way to infinity. And of course, typical questions are short and long time existence, regularity, asymptotic behavior, etc. All right. So let me just start by recalling some old work on the mean curvature flow on graphs. So actually, this is the only flow that has been studied on graph, at least in the classical geometric flow case. Of course, there are other there are a lot of geometric equations that have been studied in the complete setting in relation to relativity or other subjects. So, but let's consider a hypersurface. This n is just a way of we parameterize, but for the moment, let's m sub t is a hypersurface which is a graph embedded in Rn+1, which moves by the mean curvature flow. So we may assume that it's a graph and in the direction of the En+1, of the xn+1 axis. In other words, it's given by just simply the graph of the function u. And of course you have, if you evolve by mean curvature flow, this reduces to the well-known quasi-linear PDE on the height function u. Right. So it's an old theorem. It's an old work. There's two works by Huisken and Ecker and Huisken in this setting. In this, there's one that involves mostly local estimates, and there's one other one that involves global estimates. But what follows from these works is the following. If you start with an initial surface, which is local ellipses, and it's an entire graph, the fact that it's a graph, it's a strong assumption to guarantee existence for all time of a smooth solution. So it's surprising because this geometric equation behaves better than the heat equation. No growth condition is assumed at infinity. So nothing, no assumption at infinity. Just that it's a graph. It's exactly. Entire means that it's defined for every x, and what they show is defined for every t as well. Right? Yes, so, okay, no. They have only done it in the case, this is, nobody knows, but they're not, so they have done it only in the case where the initial surface has a conical behavior at infinity, in which case they have shown that if it's sufficiently close to some cone, then it converges to one of the self-similar solutions. The rest is completely open, and actually you don't really know what's going on. I think mean curvature flow, you can have all sorts of scenarios happening, and nobody has done. Okay, that's not true. Some people have done something on domains, etc. But the complete picture is they don't know. We don't know.
I would assume that it will converge back
to the plane. Okay. Yeah, so that's what we prove in the inverse mean curvature flow. But it's, we don't know what's going on because mean curvature could have, many weird things may happen. Yes?
But the heat equation with no control on growth has no uniqueness. So is there a uniqueness?
Okay, very good. The uniqueness is not known. I think if the initial surface is convex, so we believe that for a very wide selection of flows, you could prove uniqueness, even for Gauss curvature, etc. Otherwise, it's not known. They don't touch the uniqueness question at all. I think even right, no uniqueness was shown. Yes, no uniqueness is known. You see, yes, and you see, for the heat equation, the way to obtain uniqueness, I mean, to guarantee uniqueness is okay. Let's say if non-negative initial data, then you have the Harnack inequality, you have uniqueness. In this case, maybe the convexity plays kind of the type of the role. So I have no idea. It's not known, the uniqueness. Actually, it's a good question. You see, like, it's such a simple flow, and we don't know about the uniqueness. All right. Sorry. So let me just go back. I just want to give an idea of the proof. I mean, okay, this is not. This is a very short idea. So, but what is the idea is the following. You look at the so-called gradient function. So, what is the? I'm looking for the right dot. Oh, here it is. So you look, I don't know if you can see the dot. Can you see the right dot? Okay, good. All right, here it is. So you look at the gradient function, which is this En+1 omega, we call it, like omega, so anyway, it's the inverse of this En+1 dot nu. And this is the gradient function. And the whole point and the beginning of it is that you can localize the bound like using the maximum principle, you can prove a local bound for the gradient function. So if the gradient function is initially bounded in a ball of radius r, then later will be bounded in a ball of radius r/2 or something. And so you can introduce cutoff function. Of course, the cutoff function has to be done in the right geometric sense, and you localize the gradient function. So then you know somehow that your graph is not going to turn vertical anytime soon. So once you localize the gradient function, then you use the gradient function appropriately to prove bound on the second fundamental form, which is again local, and it's independent of the initial data. This is done with the maximum principle on the right quantity. You always, the trick here is always to find the right quantity. So you multiply the second fundamental form by a function phi of v squared, the v, this is the gradient function square, multiplied by some cutoff function, and this phi of v square, for you that they know, is this Caffarelli-Cohn and Nirenberg trick to push the estimate a little bit. So it's like a little, it's chosen, so you have to choose appropriately this phi of v square, to which you apply, multiply the second fundamental form to create a little bit negative quadratic term, which will allow you to pass cutoff functions and prove existence existence of a smooth solution independently of the initial data. So at the end,
independent for any given time, right? So as time goes down to zero?
It will, of course, it deteriorates, yes. Sorry, I had a slide where I was explaining more about it, and then I removed it because it was getting too long, the talk. I should have I should have kept it. Anyway, all right, I think I made a mistake. I moved the other way. Okay. Now, so what I would like to discuss today is whether such results extend to other geometric flows. In particular, I chose to talk about the inverse mean curvature flow and the Gauss curvature flow. The reason I chose these two examples is because the inverse mean curvature flow is an example of fast diffusion, and actually ultra fast diffusion, as you're going to see. And the Gauss curvature flow is an example of slow diffusion. So for us that works for the porous, so some of us that have worked with the porous medium equation, so you have the heat equation, and then you have the porous medium equation, which is du dt Laplacian of u to the m, where m is positive, where you have slow diffusion. Somehow things do not diffuse so fast, and then you have when m is less than 1, the power is less than 1, the u dt is Laplacian u to the m less than 1, you have fast diffusion. The diffusion propagates very fast. So this is fast diffusion, actually this is ultra fast diffusion, and Gauss curvature flow is slow diffusion. So let's start with inverse mean curvature flow, which is fast diffusion. So let me just first introduce what is the inverse mean curvature flow. Right, so let's see. Do I have where is my, sorry. Okay, here we are. The inverse mean curvature flow. I keep somehow passing some slides. So anyway, so what is the inverse mean curvature flow? Again, here I'm not very good in making pictures, so everything looks convex. Not compact, it will change the compact, but convex. So, but it's not necessary to be convex, it has to be mean convex. H has to be positive. But if it's convex, then it has to move outward. So this is the right, the right direction of a normal vector. So the inverse mean curvature flow is the evolution of a hypersurface by 1 over the mean curvature. Now in the mean curvature flow, something convex shrinks And in the inverse mean curvature flow, something convex expands. That makes the problem to be parabolic, right? It needs to go outwards. And we need to have H positive or at least H bigger than or equal to 0. Otherwise, the flow doesn't make sense. Okay. Now, just some old results. So this flow was first introduced by Klaus Gerhardt and I think later Urbas. They, in the compact case, and they showed that if the initial data is star-shaped with respect to an origin and has H positive and let's say smooth, then there is long time existence of the flow now because you don't shrink, you expand. And as t approaches infinity, the solution becomes more and more spherical. So you converge to the sphere. Oh, that's right. I forgot Garros. You are absolutely correct. Yes, I forgot Garros. Okay, right. Yes, it's just that in a little bit of mathematical context, but I knew about it. You are absolutely right. Now, so the fact that it's star-shaped, we're going to see actually plays a little bit a role, as in the previous result I told you, the fact that it's a graph. It gives some structure in the compact surface, and it makes it implies a long time existence. Now, in general, non-star-shaped initial data may produce singularities, and Smochik showed that singularities can occur only when the mean curvature goes to 0, which we expect, of course, because if H is positive, then the PD is strictly parabolic, and parabolic regularity gives us smooth solution. Now, Huisken and Ilmanen developed a level set approach for a notion of weak solutions, and the idea of these weak solutions is to allow jumps whenever H becomes 0, to allow jumps and somehow jump to something where H positive and continue the flow. And the reason they did that is because they had in mind to prove some energy estimate on general relativity, in particular some form of the Penrose inequality. For compact, yes. So for now we pass to non-compact. Okay. Before I pass to the non-compact, though, I would like to mention another result of Huisken and Ilmanen, where they take a classical approach to inverse mean curvature flow, and I will tell you what they do. But before that, all right. Before that, let's just show you which are the main evolution equations here. So what is the evolution equation of H, of the mean curvature? The mean curvature plays a role, of course, because we want to show that H doesn't get 0. So we need to control its evolution. So you see that it satisfies this equation. So if we didn't have this negative H squared over H, would be an ultra-fast diffusion equation. So it's like a dH dt is minus Laplacian to a negative exponent. And this only makes it worse because it reduces. But not so bad. This negative sign is not such a big problem, because if you have a star-shaped hypersurface, which means that this guy has a sign, then you can combine the evolution equation of the two, and this positive term kills this negative term, and for the product, you end up with this very nice PD. Again, of course, this Laplace and this gradient are in the background, in the metric, on the surface, but that's not a problem. We are doing a geometric problem. Of course, that's the right setting. This f dot nu is a coefficient that is controlled in principle for star-shaped hypersurface, and you end up with a nice ultra-fast diffusion equation. For me, okay, it's that. So Huisken and Illmanen then proved a result which is in some, for compact hypersurface, which in some sense is, it has the same feeling or the same spirit as the Eckert-Huisken result for graphs. So it says that the fact the star shapedness is a strong condition that guarantees that you not only get a solution, but you get a smooth solution. In other words, H, even if you start with some, this is a compact. You start with a compact hypersurface, which may have flat sides, for example, so H may be 0. Then they prove a lower bound from below for T positive of H. So H, you see this is a positive number, and this H depends on these two numbers, and these two numbers have to do with how star shaped, it has to have to do with the star shapedness of the hypersurface. So if the initial hypersurface is star shaped, this means that f dot nu, f is a position vector, dot the normal vector is bounded from above and below. Now, because of this equation, then the maximum principle, this is controlled from above and below for all time. All right, maybe it deteriorates the bound from above, but it's still controlled. And once this is controlled, we can get a bound from below on H.
Not only star-shaped, but also H.
Yes, you need to have H, you know, in this flow, you need to have H bigger than equal to 0. Now, you may have H equals to 0, but in the case of star-shapedness, it immediately jumps and becomes positive. That's the idea. And now, for me, they are proof. So in this proof, they don't use a maximum principle, they use integrals. But for me, this is very natural because I have worked in the porous medium equation, and this is what we do. So what they did is they take this nice quantity h f dot nu that you remember satisfies this ultra-fast diffusion equation. And you want to show that this becomes instantly positive, which is equivalent to saying u, which is its inverse, become instantly bounded to obtain an L infinity bound from above. And the inverse of this quantity now satisfies, this is a positive exponent, now kind of a porous medium, slow diffusion in some sense, because it's the inverse. And so it's a porous medium type of equation, where you can establish by using a Moser iteration or Stampakian iteration, and where the Sobolev inequality here is substituted by the Michael-Simon-Sobolev inequality, which is the corresponding thing on manifolds. And by using integrals, you can show that somehow the diffusion here helps you to get better. All right? So it's not a maximum principle argument, it's integral argument. Although a student of mine very recently, to our surprise, showed that you can even do it with a maximum principle. So he found a very good, right, the magic quantity that. Now, all right. So once you have a bound from below on H, then of course things get better. We all know that things get better because 1 over H now is it's at least it's bounded from above. And then you need to show that of course you need to bound the second fundamental form to get a C2 bound. And the way they bound the second fundamental form, it's again by this time is with the maximum principle. So the second fundamental form satisfies this evolution equation, which they combine with the evolution equation of H because they don't like this plus, and here now the minus helps. and they find that this matrix here satisfies, different equation where you don't have this term, this zero-order term. And if they do a careful argument, maximum principal argument on the maximum eigenvalue of this matrix, and they show actually that you can bound the maximum eigenvalue in terms of the lower bound of H, all right? Theta 1 has to do with the lower bound of H, the bound of H from below, away from 0, and T, 1 over T, of course, because everything deteriorates. So this is kind of a nice maximum principal argument, a quantitative way of showing something that we are expecting, that once you have a bound from below of H, parabolic regularity kicks in. All right, so this, so far, has to do with compact surfaces. When you apply the maximum principle, you apply the Michael-Sobolev inequality, you don't need to localize, so everything here is compact. All right, so, sorry, wrong direction. All right, so this is, all right, remarks. Okay, yeah, and so this is, so just here I put the name of my student who actually showed it with the, showed the result with the maximum principle. Anyway, it was, so now, so the rest I will discuss for the inverse mean curvature flow is joint work with Gerhard Huisken. And in this case, we looked at the entire graphs moving by inverse mean curvature flow. Now, in general, we didn't assume convexity, although in one case, in the most interesting case, which is the case of the cone, we had to assume convexity, although we believe that it's not necessary. So we consider an entire graph, again, like before, which in the direction of this omega is En plus 1, which moves by inverse mean curvature. So if it's convex, it will move outward. And if it's convex right, so I will describe this cone for the moment. There's no cone for the moment. We'll talk about the cone a little later. But the idea, again, for any entire graph, you would like to discuss the you would like to look at the inverse mean curvature flow. Now, the reason we started looking at that is because long ago I have done some work with Manuel Del Pino on these ultra-fast diffusion equations, and of course we saw that H satisfy an ultra-fast diffusion equation. And in this work we saw that on the non-compact case, the infinity, because you have ultra-fast diffusion, plays a weird role. And, for example, without assuming some radial symmetry near infinity, you could have instant collapsing of solutions, etc. So we would like to see with Gerhard in which sense the geometry here is helping us. And also we hope to find some applications of this in the future on other on maybe physics, etc. So anyway, so the first result has to do with initial data with superlinear growth at infinity. So we are assuming that we have an entire graph so that u goes to infinity and du goes to infinity. And we also assume, you need to assume some star sameness condition, and because here, when you have any reasonable hypersurface at infinity, which is a graph, H decays. H at infinity will be going to 0 if you have, like, for example, something that grows like a power, etc. So H will, for something that it's a graph, H will be decaying like 1 over mod X. So you need to multiply by something that so we assume some sort of start sameness condition which says h multiplied by f dot nu is bounded from below away from 0. So this plays somehow the role of the start sameness condition in the compact case. It just have to right. And then under these two conditions, we show that there exists an entire graph solution that becomes instantly smooth, and it's defined for all t positive. Now, but the difference between this theorem and the theorem of Huisken and Ilmanen is that here we're assuming that h is positive at time t equals 0. Now, I don't think this is necessary. I think you can assume that h vanishes, at least on a compact set, at t equals 0, and the same student of mine recently has dealt with this situation, that, again, diffusion helps you and become instantly positive. But here you have to worry about infinity. Now, so this somehow it's not a difficult result to prove. I mean, so how do we construct the solution? We approximate by compact surfaces. So we go very far at infinity, we cap it, we smoothen, and we approximate, and then we show that the start sameness condition is preserved, and then we use something that it was known already, a localized bound on the second fundamental form in the inverse mean curvature flow, which was done under the assumption that h is positive, otherwise it's not true, which was done by a student of Huisken Heidush. Now, yes, question?
Superlinear growth you need to find.
Yes, the superlinear growth we need for many, because actually it's not true if it's not. So the interesting case, actually, it needed, the reason, okay, this result, of course, you want to know what's happening with superlinear growth. Actually, one of the reasons we wanted to do this problem is because the interesting case, I think, is more this, where you don't have, you converge to the plane in finite time, and and you need to approximate by something to construct your solution here. So if it's not, so the answer to your question is we need the superlinear growth because under linear growth you have finite time existence. So the superlinear growth guarantees that the solution will exist for all time. There is also another reason, little technical, why the problem in this case is much harder that I'm going to discuss, because if you have something of a linear growth, this f dot nu now it behaves like a constant. For something which is conical, right, f dot nu is like a constant. It doesn't have a growth anymore, right, in x. And so h multiplied by f dot nu will not be bounded away from 0, and therefore this start sameness condition doesn't exist, and it doesn't make sense. Therefore, it makes the problem much harder.
Can you say that for superlinear growth, the problem is effectively compact?
Okay, what do you mean effectively compact? Because yeah,
as if it were compact.
As if it were compact. Okay. Right. Okay. In some sense, yes. In some sense, no. All right. But it's definitely, in terms of difficulty, level of difficulty, yes. All right. Yes. That's a good question. So what here we have some nice self-similar solutions. So here we were able to construct, to show the existence of self-similar solutions of so-called second kind. So they are of the form xn plus 1 is e to the lambda t, some profile u, x e to the negative lambda t, something like that. And for different parameters lambda, And these solutions U of x as x approaches infinity behaves like x to the q, where q depends on lambda, and for lambda in the whole range, which covers all positive exponents. So we do have a candidate for the behavior. And so we think that if you make some assumption that, let's say, your initial data is between two solutions that behave like mod x to the q and mod x to the q plus a constant, or x to the q plus lower order, then maybe it makes sense to show that after rescaling you converge to one of the self-similar profiles. Right?
One cannot move straight away, but after rescaling there will be somehow some
okay, I mean, nobody has looked at it, but here, because you have ultra-fast diffusion, things tend to mix up and get nicer results. So I wouldn't be surprised that some results like that hold, and it will be interesting to see. But we just proved this result a little bit ago, so we haven't looked at that, but definitely it makes sense. Now, let me now talk about this case, which somehow is the critical case. So for this purpose now, I'm going to assume convexity. We don't know the result if it's not convex, although we think, so there's a technical reason why we need convexity, but we think it's not necessary. So we will be assuming that our initial data is lies between two cones, two radial cones, for the purpose of this talk. I don't think for the purposes of this work, but you don't need to be radial cones. I think you can prove a similar result. Of course, I'm not saying our methods apply, but you could ask the same questions if you have a different cones, right? A convex domain across R. So anyway, but it was a little tricky even in this case. So let's assume that you have some initial data that actually I'm going to assume that I take a radial cone, and I'm having an initial data that lies between this cone and that cone plus a constant. The reason I need to put such strong conditions is because I want to prove a strong result, right? I want to show exactly what is going on in this case. And I want to show that actually the cone at infinity really determines everything here, all right? And the reason for that is because you have ultra-fast diffusion, so information passes very fast. Okay, now, let's see the PDE. Take a little look at the PDE. Now, if you use the height function as a graph, as a function of x in Rn, then it's inverse mean curvature, so this is the equation. So in regular mean curvature, you have this on top. So it's fully nonlinear instead of being quasi-linear. Now, although I love looking at PDEs, unfortunately, in such cases, it's better to use a little bit the geometric equation and not just the PDE when you compute. So we will be using geometric quantities rather than U. All right. So let's look now for solutions, for self-similar solutions. So there are the self-similar solutions I talked about, so that they have superlinear growth at infinity. But in the case of linear growth, you have solutions that they are much simpler, just separation of variables. Radially symmetric, so they are of the form a function of t mod x plus, of course, any constant. And alpha satisfies an ODE, which wants to make it vanish in finite time, depending on the initial angle. And of course, the theorem that you want to show is that if you have an initial surface that it's trapped between a cone and its translation, then this cone, the solution exists and up to exactly the same time, and it becomes flat at time capital T. So this is more or less the theorem. All right? And now let me just, so we do it, of course, in always the two steps, short time existence and long time existence. Short time existence is very simple because you approximate by the ones with superlinear growth, and then we show that something is preserved for a little bit. Now what is harder is to show that your existent time is exactly the one of the cone. Yes? Sorry, flat means, this is not, flat means very flat, means that they become, flat means that they just become the plane. Infinite, because the solution of the ODE, the angle, right, the angle decreases.
Alpha T plus whatever alpha T is minimum, but 2. Goes down flat really fast.
Yes. It wants, yes, so it becomes flat. All right. So, okay. So now for like short or long time existence, our initial assumption, as I said, is that the initial data is trapped between the two cones, radial cones of the same aperture. Again, you don't need to have radial cones, but we don't have a theorem if they're not radial because we only did the radial case. But we need to have the same cone if you want to prove the result that you prove. Otherwise, the result is not going to be as good. All right. And now we need a little bit of a technical assumption here that, again, as I told you, H, you expect in any reasonable hypersurface, H to decay at infinity is like 1 over mod X. Now, the height function on something that grows linear, it grows, of course it behaves like mod X. So you expect H multiplied by the height function. This F dot En plus 1 is just U, right, in the geometric parametrization. So this says that somehow H multiplied by U near infinity is bounded between constants. Now, we make the assumption that this also holds on compact sets, although again, I don't think this is necessary, and I think the same student of mine removed this assumption. So you can allow H to vanish on compact sets, like in the compact case. So anyway, and so now, of course, you know that the maximum principle, the comparison principle, tells you that U all the time will remain between these cones. Now, the hard part, of course, is to show that H is not going to go to 0 too fast before the cones become flat. All right, so this is, and okay, So, all right. So again, so for short time, you can find the right quantity and apply the maximum principle and show that for a short time, your H dot F dot omega will remain bounded from above and below, just using the maximum principle. But for a long time, the maximum principle doesn't work. It doesn't give you the maximum principle. That's okay. For some time, you will be all right, but not the precise result. In the precise result, you have to use infinity in a very precise manner. All right? Okay, so what we do, so we use the diffusion again and integrals, etc. But the hard part is just, okay, so you look at V, our quantity V is H multiplied by F dot omega, which is the height function. So H multiplied by F dot En plus 1, the height function, now you expect to behave like a constant at infinity. And then we have to multiply by this gradient function, more or less. This is the inverse of the gradient function. So this is that. Which doesn't do anything. Near infinity is bounded from above and below. But all this product here has a better, if you just take the product, everything together, you don't have a positive term you somehow kill this term. You want to take this omega dot nu n plus 1 dot nu to kill this term. So anyway, it's a technicality. So you consider this quantity, and now here is where convexity comes. When we consider this quantity, we get this term, and remember, you want to show a bound from below on V. So if this is not convex, then you may have this may be negative, this may be going to 0, and you're in trouble. So this proof doesn't work. Although I think we think that unless we're missing something, convexity is not necessary. So anyway, so the basic step here is to show a bound from below on H, given the fact on V, which is H appropriately multiplied with the right quantity. And of course, you need to work with the non-compact space. So, okay, so what do? We look at the inverse of this quantity, and you want the bound from above on W. So you want to bound the infinity norm of W. Now, you know that for your short time existence, because you can prove very good estimates at infinity, W behaves like a constant, not exactly like a constant. It has exactly the same behavior. It behaves like gamma of t, where gamma of t is exactly the same behavior as if you had the cone. The reason for that is because you prove the right C2 alpha estimate in the right weighted spaces, which tell you that W has the right behavior at infinity. Hence, we can subtract from W the behavior at infinity. And if you subtract the behavior at infinity minus plus delta, and you take the positive part, you make W compactly supported. And that's important because you want to use some Harding inequality, and you want to integrate, to be able to integrate, right? So again, we want to show that we want to establish a bound from above on W, all right? But using, let's say, a Moser iteration or some packet iteration, but where you cannot, of course, a local bound is obvious in terms of the L1 bound, but the problem is to find the L1 bound, right? All right. So the first step, which is and the L1 bound actually, or the LP bound, actually, you can just take P equals 1, is the hardest part here. Because once you have an L1 bound, then you can, a global L1 bound, then you can do a Moser iteration argument appropriate and get an L infinity bound. But again, it will not be an L1 bound on W, because W behaves like a constant at infinity, and you cannot integrate on a non-compact space. So what we do is we subtract the behavior at infinity minus something a little bit, plus something more, to make W hat compactly supported, but of course we have no information as of the size of the support, right? Okay. And once you have this, you combine energy estimate with the Harding inequality, the right Harding inequality, which states this, right? So that you can, if you have, you are in complete non-compact space, and you have a compactly supported function, sorry, it's not space, it's manifold, and you have a compactly supported function G, you can bound, this is G squared, in terms of, this is the position vector. And this is exactly how it matches. It matches perfectly with our setting with whatever we have and whatever we multiply to do it. So once, so you establish then an L1 bound on W hat, with global L1 bound on W hat, which in turn gives via Moser iteration argument a local L infinity argument, and therefore a global L infinity bound on W. And W is more or less 1/8. And once you have that, then you are in good shape. And for how long you can do this bound? For as long as you have the right behavior at infinity, because this is what you subtract to get a compactly supported. And so you show, like, you have your short time existence, and the whole point here is if you want to extend your flow up to the crucial time, capital T, and the moment you argue that at your maximum time of existence, which you don't know that it's all the way to capital T, you still have the right bound on H inverse, and you can continue the flow. Of course, you need to argue.
The focus to me is argument mode. I'm going to use the argument mode in a different.
Okay. It's like a Poincaré. It's kind of a point. Yes. All right. Or not Poincaré. It's Poincaré. Okay. All right. Okay. All right. Let's call it like Poincaré. Yes, it is Poincaré. Actually, you're right. But okay. What are you used in for?
It should be one on some distance. Because it's damage. On the left-hand side.
Yes, f goes to infinity. F goes to infinity at infinity. F is a position vector. F is a weight, so it's a weighted Poincaré. It's a right.
Now I see it. So you absorb F into something, and on the right-hand side you'll have one over X.
Yeah, to prove it, actually, it was done before, but I couldn't find the exact reference. To prove it is very simple. You just use integration by parts. Right.
This is
okay. All right. Good. All right. And that proves the theorem. Okay. So that proves a long time. So at the end, you have, of course, to combine your a priori bounds with. We use a result that was already available by Buji Tian and Sujia Wang, which says that for any fully nonlinear, not any, but the right kind fully nonlinear equation, parabolic operator, once you control the coefficient somehow, right, then you get C2 alpha a priori bound, so that gives you the regularity you want. And now, okay, now, and as I told you, like for me that I've done some work in the past, my thesis was on porous medium type of equations. There's definitely a lot in common. Of course, this is in a geometric setting. So what makes this problem much harder is that you don't have a Harnack inequality for H. And in the case of the porous medium equation, or the fast diffusion, for any M actually, you have the so-called Aronson-Benellan inequality. Now, this holds for M less than 1. This inequality holds for any M less than 1. But somehow this inequality for our are a little bit familiar with differentiable Harnack inequality, plays a little bit the role of a differentiable Harnack inequality, and that somehow helps, right? It's a pointwise inequality, but still helps. And now, unfortunately, for the inverse, I try to show something like that for H in the case of the inverse mean curvature flow, but I couldn't, and maybe it's not true. And one of the difficulties for the inverse mean curvature flow is that you cannot scale time. So there's no way you can scale time. So you cannot say, for this porous medium equation, scaling, they have a very rich scaling property. So it's scaling, you can scale a lot of different ways, the space and the time. But for the inverse mean curvature flow, you can scale the space, but you cannot scale the time. Yes, no.
I don't remember that for fast, ultra-fast, there is some inequality, like Harnack inequality, which makes it a global existence.
We have. Right. There are, and actually, now they prove, and vice versa somehow, right? They prove also, they use these equations to prove. But what we have, Yes, but not all the time. You mean, okay, for which M? M negative or M? Positive. Yes, yes, absolutely. When M is positive, then yes, it's true. Our case M is -1, and actually, it's what happens in this case. If you start with the UDT equals minus Laplacian U inverse. Because of ultra-fast diffusion, if you start with something which is in L1, you get immediately vanishing because there's so much diffusion, you don't have enough mass at infinity, and then immediately goes away. And so in order to have existence, you need to have enough growth at infinity, which is exactly this linear. So the critical case for M equals, in our case, M equals -1. So the critical case, in this case, it's the linear growth. So it's really there's very much in correspondence what happens in the ultra-fast diffusion on Rn with our case. That's a good point. Actually, we would have liked to use, I don't know, because I don't know if the people have used the ultra-fast diffusion for Harnack inequalities on Rn. But we were hoping to use our inverse mean curvature flow maybe to prove some new inequalities. But we haven't done it yet. Right. So, you know what? All right, how have a talk? So, it's for, I think all my time is up. Okay, so maybe we can stop with half of the talk. So the open, right? It's up my time, right? So just start with okay, some open problems for the inverse mean curvature flow. Okay, one problem is the asymptotic behavior. Because it's ultra-fast diffusion, maybe we can say something nice. And then, of course, as I said, remove the convexity. And also, for me, okay, for being an analyst, I would like to remove that H is, to be able to start with an initial data where H is non-negative, right? What happens if you start with something which has a flat side? Does it become immediately positive? What is the effect of infinity in this case? Okay, this is, right, in the case, the compact case, we saw that immediately becomes positive. And okay, it would be an interesting, somebody could prove some sort of Harnack inequality. There is some sort of, that somebody has done, I forgot who has done it. Somebody has done a Harnack inequality for inverse mean curvature flow, but it's not a very good one, I think. Like, it's not a good, it's not a, at least, it's not sharp, because, you don't, the problem is that, because you don't have the scaling. Usually these Harnack inequalities use the scaling, and you don't have the scaling. All right, so you're not going to find out about the Gauss curvature flow, but that's okay. I'm sure you're happy to stop here. Yes.
First of all, I think usually I can absorb only half of the talk, so this is a very good time.
Yes.
My attention so the question is either kind of monotonicity formula of some entropy inverse mean flow.
Not exactly in the sense of mean curvature flow, where you have this very nice monotonicity. It's not a gradient flow. Yes. Okay.
H squared.
H squared. Yes. Yes. It is true, but right. This is true, but it's not like there's no monotonicity formula in the sense of right? Yeah, there's a monotone quantity, but not in the sense of the Huisken phonotonistic formula, where the DDT of this gives you something negative and yes, and then you show the convergence or something.
Derivative, time derivatives of local quantities bounded in terms of the slightly larger local quantity. This is your
yes, it's a monotone.
Interrelation. Oh, I see.
It's only two-dimensional surface, three-dimensional.
Yeah. Yeah, I mean, you can. H satisfies a very nice, PDE, and you can do the DDT of H squared and integrate by parts, and you get a nice cancellation.
I have a question about the second half of the talk. But the famous thing about the porous medium is that there's no exclusion.
Yes.
So it strikes me that if you have, if you're talking about positivity of H, okay, well, we're in inverse domain. We can go to the second part.
Yes. You missed. You missed a lot, I told you.
And there's a smoothness question. You're not going to have smoothness here.
Yes, so you missed a lot. So, no, okay.
Second hour, right?
Yes. Yes. No, so yes. So recently, yes. So, okay, I'm just going to tell you the second part of the talk in 1 minute. Okay, I don't want to take 1 minute. So 2 points. Points. Okay. Number one is that it's exactly the opposite of this in the sense that we can localize everything. Okay. For the Gauss curvature flow, for example, we can localize everything, which is in contrast with you. So it's somehow in the spirit of the mean curvature flow, but it's with a lot of hard work, and show that if you have something that is a graph or even a graph of a domain, remains a graph, and you have long time existence. In this case, we can deal with any convex hypersurface. Of course, it's Gauss curvature, so you need assumption. Any complete non-compact convex hypersurface, whether it's a graph over a domain or it's a graph over half space or whatever. We know exactly that you have long time existence, and it's nice to know, and you can localize everything. So there is where slow diffusion helps you, that you can localize away from infinity. But you don't have regularity, and in 2D, the optimal regularity is C11. And we have shown, long ago, I have shown with video solving that in higher G, you have C1 alpha, although not exactly all the times. And recently, we have shown that it's C1 2 over n is the optimal regularity. In the case you have solutions with flat sides in higher D. And so, okay, my minute is up.
That means you can evolve to something which has a flat side.
Yes. So something we did long ago with Hamilton is we looked at the evolution of things with flat side by Gauss curvature flow. And we did 2D surface in R3 just for simplicity. And in this case, you saw that the boundary of the flat side is exactly like in the porous medium equation, becomes smooth instantly and behaves like a free boundary which propagates with finite speed. And at some point, the flat side disappears before the surface disappears and becomes 3D complex. And recently, in higher D, Gauss curvature flow is much harder. 2D Gauss curvature flow is much easier, or Mons-Ampere equation is much easier. So we recently showed with one of my students that the same thing happens in higher D. The long time existence is a problem. Like if you start something that has a flat side, the flat side remains. And we do that with maximum principal arguments, but they have to be very sharp. Okay, I told you everything.
So one thing, but interesting because if one were to do the manifold, for example, the compact, maybe with this one, if one wants to do the manifold, what sign of curvature? So if you're
on the space.
What would help?
That's a good question. I think there have been some. I think there is a work of Mutawan and Brendle, and I think they do it with some manifold hyperbolic that they look like hyperbolic at infinity, and I assume that helps. But
it gives you an extra problem.
Yes, yeah. But I think they only assume it at infinity, I think. Yeah.
If there are no more questions,